So if you're in Chem 30, you might be starting the introduction to thermochemistry. So I'm just going to go over the topics like endothermic, exothermic, and then do a couple examples with the Q equals MC delta T formula and calorimetry formula. So taking a look at this, the first thing you learn in thermo is that all energy originates from the sun. This is going to come up time and time again, right? So it might be big, long questions, and then something very simple like, where did the original source of energy come from? You want to choose the sun. Now this order, sun happening, so I say let's draw it just like for a way to help remember it, and I'm not good at it. So the sun causes that's where the energy comes from. Then you have photosynthesis. So something needs to capture that energy. So flowers, plants, anything, that grows, and then things need to die. So bacterial decay, I'm not sure how you'd show that, but essentially like a dinosaur or something. I don't know why that's a dinosaur, just it looks like a number 2, but something's going to die. And then after a very, 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 very long time, you are going to extract it and get crude oil, and it can be used for things like driving a car. So you do want to know this order. Again, it comes up. It should be a nice, simple question. And if you have tried old diploma questions, you probably would have seen questions that are similar. Now, moving on from there, we start to talk about endo and exothermic. So starting with endothermic, this is when you are gaining energy for a reaction to happen. So your energy has to be a reactant in this case, and you absorb energy from the surroundings. Furthermore, the surrounding temperature is going to decrease. So a perfect example here is photosynthesis. And this is just showing any endothermic reaction where you have reactants and energy is on the reactant side and you get products. So here is your example with photosynthesis, and it's just showing that it's an endothermic change. The opposite to that is exothermic, which produces energy. So that you'd see energy on the product side. It's going to cause your energy of the surrounding to warm up. And an example here is like cellular respiration, or another big one is combustion that often comes up. So this is another reaction you want to memorize. So cellular respiration and photosynthesis. Now I just wrote a little bit more here just to make sure we really understand endothermic and exothermic and how it affects that environment, just touching more on what we just looked at. So exothermic, I think one of the best examples is combustion, like what we're seeing here, where energy is given off. These are just arrows. And then that means that heat has to go somewhere. So the resulting area, your temperature is going to increase. Endothermic reactions, on the other hand, take energy from the environment. So the energy the temperature on the outside of the environment gets hotter. So here, this is just a very, very simple example, an ice cube melting. So heat has to come in from the environment to make this ice cube melt. And if that's happening, that means that heat's being used up. So your temperature of that resulting area has to decrease. Now that moves on to energy changes. And this is the formula Q equals MC delta T. Q is given in joules. Your mass is in grams. C is specific heat capacity, and that unit is joules per gram degree Celsius. And then your temperature is in Celsius. Now, the biggest point here is that this is when you're heating or cooling a substance. It's not a chemical reaction. So you know you're using this because you're just heating or cooling, say, aluminum, right? Like it's something that is going up or down, but you're not involved in a reaction. So here's some examples using Q. So we're going to use that formula on all these. Q equals MC delta T. And just one more note here is that when you're looking at water, 1 milliliter will equal 1 gram. So if we need mass in grams, but you were given liters, we can just exchange that unit. So if I'm starting with this one, and the answer is given here, but if I want to know the quantity of heat, I'm solving for Q, and you're given liters. So we have M, you know the specific heat capacity of water. We can also look that up in our data booklet, and we know our temperature change. So let's set up that formula. So you'll have Q equals your mass, so 1.50 liters but that needs to be changed to milliliters so that we can say it equals 1 gram. So we're going to multiply that by 1,000 because there's 1,000 milliliters in 1 liter, and then liters will cancel. Then you can multiply it by 4.19 joules per gram degree Celsius, and then you can multiply by your temperature change. So 98.7 minus 18. Plug that all into your calculator. You'll get one very large number. We have 507,199.5. Now, based on what we're seeing in terms of our units, your energy is in joules. So if your number's fairly large, oftentimes we'll just divide by 1,000 and change your units from joules to kilojoules, because there are 1,000 joules, if I'm saying divide by, in 1 kilojoule. So your joules will cancel, and we'll get that, sorry about that, and we'll get that value that we see here, 507 kilojoules. And notice that also follows your significant digits, right? You're given 3 in all of these, so you want your answer to have 3. The next one with determining the specific heat capacity, this time you're solving for C. And you have everything else. Now it gets a little bit confusing because your unit here is in megajoules. We're going to have to change that to joules. So we'll have, it's also saying that this amount was released. So we can view that value as being negative, right? Because it's heat given off. And we see more about the negative signs with endo and exo. So if this doesn't completely make sense yet, that's okay. It will as you move on in this unit. So you'll have negative 0.72 megajoules. And there are a million joules in 1 megajoule. And we're going to multiply this, this equals, because that will be your Q value altogether, your mass, but your mass is in kilograms. We're going to have to multiply this by 1,000 to get to grams. So kilograms can cancel, times C, which we want to solve for, times your temperature change. And your temperature change is going from 350 to 15. So 15 minus 350, right? Final minus initial. Now, with all of that, we want to isolate C. So get C alone by dividing the other numbers to the other side. And if you do that, you get C equals 0.8597. And with following our 2 sig digs, we will end up rounding that to 0.86. And the units for specific heat capacity are joules per gram degree Celsius. So those are a few harder examples for Q, but it's still following the same thing. The easier ones, you don't have any extra conversions. You just plug it in based on what's given. Okay, so then once you've learned that, the next part that you probably will move on to is calorimetry. And this is an experiment you can do, right? It's a device. So this would be a calorimeter. It's a device that measures energy change. And how it does that is it takes what Q would give you, right? And this is going to be about the water. And this part here is going to be about your reaction. So whatever amount of heat is given off from the reaction will go into the water, or whatever amount of heat is absorbed from the reaction came from the water. So these two are related and we can figure it out. The other part with this though is that there's an assumption that your calorimeter will not gain or lose heat. Now with combustion reactions, because they give up so much energy, a lot of times your calorimeter will gain heat. So in that case, this would be called bomb calorimetry. The beginning stays the same. The NH is still about your reaction. This negative MC delta T, that's going to be about your water, but this added on negative MC delta T is going to be about your container. So you're taking your container into account. So when it says M, that's mass of the container. C is the specific heat capacity of the container. And your delta T is the temperature change of the container. If a question doesn't give you that extra information, you can assume that this delta H from the water and this delta H, but delta T from the water is going to be the same in the calorimeter. So looking at a few questions here, again, so continuing with this last slide, just going over some calorimeter examples. So this one we have, we know it's calorimetry because we are using a calorimeter, and so you'll have that formula NH equals negative MC delta T. And from the previous slide, we saw that this left-hand side is about the reaction, the right-hand side is about the water. So when we're filling this out, we can start filling some information in. You have 8 grams of ammonium nitrate. So that is our starting point. And we need moles, so we're going to multiply this by the molar mass of ammonium nitrate. All right, so that's NH4, nitrate is NO3, and we'll add up 2 nitrogens, 4 hydrogens, and 3 oxygens, and you will get 80.06. Now we multiply this by H, and that's what we're solving for, the molar enthalpy, and that's going to equal negative MC delta T, the information about the water. So it tells you 1 liter of water, so we want to remember that 1 liter, usually it says milliliter, 1 milliliter equals 1 gram. So 1,000 milliliters are in 1 liter, so I'm going to replace this with 1,000 grams. We could assume, because it's water, we know that we'll always have that specific heat capacity. And then lastly, your temperature change from 30.39 minus 21, final minus initial. Now, solving for H, we want to isolate H on the left-hand side. So we can keep this together and just divide it over. And so get your value on the right-hand side and then divide it by the amount of moles. And you'll see that H will equal a pretty large number, negative 393.736. And this would be joules, right? Because this is going to be a molar enthalpy, so joules per mole. And that's based on the joules from our unit, specific heat capacity. If this is a large number, again, we'll often change the unit to be in kilojoules or megajoules. And now that's why we're seeing this value, negative 394 kilojoules per mole. And that's your final answer for that first one. Looking for the next one, asking about how much propane, and we want it in grams, would have to be burned in an open system to raise the temperature of 300 mils of water from 20 to its boiling point. So there's a few things we're assuming here. One, that we're solving for N, and then we'll change it into grams. They also are giving you the molar heat of combustion, so we can fill that in, negative 2,043.9 kilojoules per mole. And again, based on the specific heat capacity, we're going to need to multiply this by 1,000 because we need it to be in joules, not kilojoules. And now that's going to equal negative 300 grams because 1 milliliter equals 1 gram times the specific heat capacity of water times your temperature change. We should know the boiling point of water is 100 degrees, so we'll fill that in. And then just like our last question, we want to isolate N, so we'll divide all of this over. So you want to get your answer from the right-hand side and then divide it by your enthalpy. And then you get your amount in moles, and the value you should get here is 0.0492. And this number keeps going, and we know we can change moles into grams by multiplying once again by your molar mass, and this time it's of propane, and propane is C3H8, and if you didn't know that, you can check page 4 or 5 of your data booklet. So the molar mass of propane is 44.11. We'll do that last multiplication and you'll see that value 2.17 grams. So if you need one more example, we can try one more here, and this one, same idea. We have grams. We want to get to moles of benzene. So you'll have 5.08 grams. Multiply it by 1 mole of benzene, which contains 78.12 grams. That gets grams to cancel. We are multiplying that by the enthalpy. So I'm just following the formula still written up here. And that will equal the information about water. So negative. So if you have 5 kilograms, that's going to be changed to grams, and that would be 5,000 grams times 4.19 joules per gram degree Celsius times your temperature change. So final minus initial. Now we want to solve for H. When you do that, you will see you'll get one very large number. So we have 3, what is this, million, 0.60597.0, and this number keeps going, and that would be joules per mole. So now if we want our unit to be megajoules, we are going to have to divide by 1,000,000. So divide that by 1,000,000, because there's 1,000,000 joules in 1 megajoule, and then you will see that answer, negative 3.06 megajoules per mole. And the per mole is just because it is a molar enthalpy. Sometimes it will just say enthalpy and you can just write down the value without per mole. It just depends on the question. So as always, I hope you found this helpful. If you did, please make sure to subscribe. And if there's any other question I can ever help you with, please just let me know in the comments. Thank you for watching.